In this video, part 2 of section 3.3, we are going to be looking at integrals that have this particular form, square root of an a squared plus x squared. And of course, take note that that could also look like x squared plus a squared. So the key here is you've got a plus sign between the two terms. The other two forms that we look at, you have a minus sign. Well, the basic substitution that we're going to do is we're going to let x be equal to a tangent theta. That is the key to the strategy. Other than that, everything that we're going to be doing is exactly the same as in the first video that I created. So this process should go a little bit more smoothly. So here's my problem. I notice that my radical is in the form of the square root of a squared plus x squared, where a is equal to 1. So we're going to do the substitution of letting x be equal to a tangent theta. A tangent theta, where a is equal to 1. So my substitution is simply x equals tangent theta, and then dx is secant squared theta. So we substitute in tangent theta for x. We square it. We know that 1 plus tangent squared is secant squared. And now we can take the square root of secant squared, and we end up with secant theta. So the idea here is the same thing that we were doing in the last video. Then we go over here, and we actually do our integrating. So we have our original integral is 1 over the square root of 1 plus x squared. So we have 1 over secant theta times dx. dx was secant squared, d theta. The secants cancel out. So we end up with the integral of secant theta d theta. And so that's a trig integral we should know, the log of secant theta plus tangent theta. So that one wasn't too difficult to integrate. We'll make up for it in some other ones. And so now we have to get rid of the thetas and go back to x's. So we need a secant theta, and I need a tangent theta. So we go to our basic identity. Our basic identity was x is equal to 1 tangent theta. So tangent theta is simply x over 1. So x is the opposite side. 1 is the adjacent side now. Remember, the tangent is defined as the opposite side over the adjacent side. Make sure that you put the quantities in the correct spot on the triangle. To find the hypotenuse, we take the square root of that side squared plus that side squared. And so we end up with this, which of course was the radical that we started with, just like in the last problems. All right, so we need to figure out secant. Secant is the reciprocal of cosine. I don't memorize secants. I just remember secant is the reciprocal of cosine. The cosine of theta is the adjacent side over the hypotenuse. So cosecant must be equal to hypotenuse over adjacent. That's one of those things I don't memorize. I figure it out. So the hypotenuse over the adjacent would be this divided by this, which gives me that. Tangent is opposite over adjacent, which is x over 1, or just x, and voila. We're done. Now that one was just too easy. Look at all that empty space I didn't use. Oh, I'm making up for it in this one. Okay. I look at my radical. Oh, I see I've got a plus sign underneath the radical sign. And 9 is a perfect square, x squared. Well, it looks like I can do a substitution here of this form. My substitution is going to be a tangent theta. A is 3. So my substitution is based on x equals 3 tangent theta. I take the derivative of that. I get 3 secant squared theta. And now I go through and I do the substitution. So I take out the x squared, the x, I put in 3 tangent theta, I square it, factor out the 9, change 1 plus tangent squared to secant squared, take the square root of the whole thing. Then I bring that all the way over here. And so I have the integral of 3 secant theta divided by x, which is 3 tangent theta, times d theta, or dx. dx is 3 secant theta. So that goes here. So we're substituting all those in. Now, how do we clean this mess up? So we have a secant times secant squared in the numerator, which is secant cubed divided by tangent. All right, so as I said in one of the other previous problems, like can we get everything in terms of the same trigonometric function? Well, sometimes you have to do a little trial and error, which, I did on scrap paper. So secant cubed divided by tangent. So I know that secant cubed, I like to get everything in terms of sines and cosines. Makes more sense to me. So secant cubed is just 1 over cosine cubed. Now, you may do it differently than I did. 1 over tangent is the same as cotangent, right? So 1 over tangent is equal to cotangent. And so cotangent is cosine over sine. So I got everything in terms of sines and cosines. Some of the cosines cancel out. I end up with this, which doesn't seem to be that helpful. 1 over cosine squared sine, which is the same thing as secant squared cosecant. And that may not seem like it helps. Now, was that the quickest way of getting to where I just got to? Probably not. After I wrote this out, I thought of another way of simplifying it to the same thing. But hey, as long as you get there. The question is now, where do we go from here? Because this doesn't look like it could be integrated at all. But this is where we have to do, I'm laughing because it's just so much fun. We have to do integration by parts. That's what we got going on here. Integration by parts. So I decided to let u be equal to cosecant x. The derivative of cosecant is negative cosecant x cotangent x. That means the derivative had to be, I put the 3 in there. I didn't really need the 3 in there. Derivative dv is secant squared. The antiderivative of secant squared is tangent. So I've got all my parts, putting them together in parts. My u times v is cosecant x times 3 tangent x minus the integral of v du. And we end up with this. And let's see, can that simplify at all? Well, cosecant, cotangent, if you play around with those and do what I did up here, is try to get everything in terms of the same trig function, you can actually get this whole thing to simplify down to cosecant. No, actually, you can probably see that pretty easily right here, actually, in this one. You got the cotangent here times the tangent times that. They're all being multiplied. Well, tangent and cotangent are reciprocals, so you multiply the reciprocals, you get 1. So that whole thing is negative cosecant times the negative 3 becomes a positive 3 cosecant. Play around with it. You'll get, some of these you're just going to have to try working out the details on your own. So we have 3 cosecant. All right, so now we need to find the antiderivative of cosecant. Well, the antiderivative of secant is the absolute value of secant plus tangent. So cosecant would be the absolute value, negative absolute value of log, negative log of the absolute value of cosecant cotangent. Well, anyway, we get that. So that is as far as I can go until I do some trig substitution. So here's where I'm at. And now I got to get rid of, oops, these are supposed to be thetas still. That's supposed to still be a theta. Don't want that to confuse anybody. Those are still thetas. That's cosine of theta, cotangent of theta. Because now we need to get rid of the thetas and go back to x's. So I didn't have a lot of room to do that. So this is the one problem where I left out a lot of steps. So I'm kind of explaining what I did, and I'm asking you to kind of go through and fill in some of the gaps. So cosecant, I need a, let's gonna go through another color. I need a cosecant. I need a tangent. I need another cosecant and a cotangent. So I need cosecant theta, tangent theta, cotangent theta. So I start with my basic identity. Tangent of theta is x over 3. I figure out what my right triangle is, and then I can figure out all of those trigonometric identities. Cosecant, once again, is 1 over sine. Sine is the opposite over hypotenuse, so cosecant is hypotenuse over opposite. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. And so you end up with substituting these back in and then simplifying it to get this. All right. A lot going on there. Okay, just when you thought it couldn't get any more fun, we can throw in some arc length. So find the arc length of the curve y equals x squared over the interval from 0 to 1/2. So the first thing you need to do is you need to come up with your integral. So remember that arc length is the integral from a to b of the square root of 1 plus fx squared, f prime of x squared. So yeah, f prime of x squared. So as I showed you in arc length, let's start over here. This is my arc length stuff. I have y, the function is x squared. So I start with that. I take its derivative. I get 2x. And then I square both sides. So the squaring the derivative, I get 4x squared. So again, arc length is the square root of 1 plus f prime of x squared. And so that gives me this. And so we're going from 0 to 1/2. Well, that's clearly going to be in the form that we're using here. So I believe when we were doing arc length, there was a problem that we did, or it could have been surface area. And I said, we don't know how to do this yet. You may remember that. There's one of those problems back then. Well, now you're going to be learning how to do it. All right, so let's go through the process real quick. So we want x, this is similar, or if not, this is similar to what I did before. We could take this, the 1 plus 4x squared, divide both sides by 4, and get 1/4 plus x squared. And so the square root of 1/4 is 1/2. So x is equal to 1/2 tangent theta. The derivative of that is 1/2 secant squared theta. Here's my original integral. Substituting in 1/2 tangent theta for x, squaring it. We end up with that, converting it to secant squared, taking the square root. Putting that in my integral over here, plus my dx is 1/2 secant theta, secant squared theta d theta. So that gives me a 1/2 comes out front, secant cubed. Well, you may remember from another previous section that we did when we were doing reduction formulas. Reduction formulas. We used secant cubed. Actually, I think we did secant cubed a couple different ways. I think we may have done it another way, but we're going to use a reduction formula. So the reduction formula that we want to use is going to be this one right there. And so I didn't actually write out the formula, but I'm using a reduction formula. And so just plugging everything in. So you can look up that the reduction formulas that we're going to want to use. And the other thing is I have to change my bounds, because in the last problems, remember we always had to go from thetas back into x's. But now we have a definite integral. If you have a definite integral, you can save yourself the bother of converting everything back into x's if you convert your bounds from x's into thetas. And so that's what I'm doing over here. All right, I'm converting my bounds from x bounds into thetas. And I'm using my basic identity, my substitution from over here, right? So if x is equal to 1/2 tangent theta, then tangent theta is 2x. And then using inverse trigonometric functions, theta is arctan of 2x. Now, what's my upper bound? My upper bound is 1/2. Substitute 1/2 in there. 2 times 1/2 is 1. I get theta is the arctan of 1, which you can remember from trigonometry is pi over 4. Then substituting my lower bound in 0. Arctan of 2 times 0 is arctan of 0, means that theta is 0. So now that I have my bounds in terms of theta, I don't need to go back and convert everything back into x's. I don't need to do the little right triangle thing. So that's what I'm using here, pi over 4 and 0. And so the rest of this is just algebraically simplifying that. The reduction formula, once you use the reduction formula, that is your integral. You've taken the integral when you use the reduction formula. Now you're just substituting in your bounds of integration and evaluating it, which of course can be a lot of fun in itself. All right, I think that's it for this video. This is another long one. And yep, we're going to get to the final third form in the last video. See you then.